Now, Sumpner's test. Sumpner's test is also called as back-to-back test. And before going to know about this Sumpner's test, the knowledge on open circuit test and short circuit test is very essential. And you must be aware of Hopkinson test, and what you must note from Hopkinson test will be discussed here. So there is no need to study the entire Hopkinson test to understand this Sumpner's test. And from this video on Sumpner's test, you will go to know why Sumpner's test is to be used and why it is called back-to-back test, and how to conduct this Sumpner's test, and how to find transformer performance, that is how to find the transformer efficiency and percentage regulation. Now let's discuss why to use Sumpner's test. Sumpner's test is mainly used to determine the transformer temperature rise. And why to determine the temperature rise in a transformer means from the safety point of view of the operating person, as well as from the safety point of view of the internal parts of the transformer, the temperature rise in a transformer is to be known. Because if the temperature rise is enormously high, the transformer might get exploded like a bomb. So is why most of the transformers are placed outdoor. And secondly, it is used to find the performance of the transformer, that is percentage regulation and efficiency of transformer. And it is studied that from the open circuit test and short circuit test data, percentage regulation and efficiency can be found, but the results that obtained are not accurate. And why percentage regulation and efficiency obtained from the test data of open circuit test and short circuit test is not accurate means, let's discuss in brief. Open circuit test is conducted on LV side with HV open, and here rated voltage is applied, and from this test the iron loss of a transformer are found, and shunt branch elements R0 and X0 of the transformer electrical equivalent circuit are found. And now coming to short circuit test, this test is performed on HV side with LV side short circuit. LV side is short circuit with a thick wire, and here rated current is applied, whereas in open circuit test rated voltage is applied. And from short circuit test, copper loss of the transformer found, and the series branch elements R01 and X01 are found from the short circuit test. And by using the test data from the open circuit test and short circuit test, the transformer efficiency and regulations are found. But the point you must keep in mind that in transformer or in any machine, if you give input, you will get output, and output will be always less than the input because of losses in the machine. And in transformer, the major losses are classified as copper losses and iron losses. So these copper loss and iron losses in transformer exist simultaneously, but from the open circuit test and short circuit test data, we are finding one loss by neglecting the other loss. That is, from open circuit test we are finding the iron loss by neglecting the copper loss, and from the short circuit test we are finding the copper loss by neglecting iron loss. So the results obtained from open circuit test and short circuit test are not accurate, whereas in Sumpner's test we will find the copper loss and iron losses simultaneously. That is, we are finding the losses which are occurring simultaneously from Sumpner's test. And the other reason why to use Sumpner's test is, if in case of small size transformer, to find the performance you will apply the input and you can connect the desired load, and by loading this small size transformer for a particular period of time, by collecting the transformer oil, you can check the temperature rise. But to check the temperature rise of large size transformers, you need to connect the huge load on the large size transformer, and you must load it for a particular period of time. That is, large size transformer will consume more input power. Whereas in this case of small size transformer, to determine the temperature rise, this transformer is consuming very little power because of very low load, and that power consumption can be neglected. But to determine the temperature rise of large size transformer, we need to apply more input. That is, here power consumption is very high as we are connecting large load. That is, here to determine the temperature rise, we are wasting large amount of power. So to determine the temperature rise in a transformer without wasting the large amount of power, we are going for Sumpner's test, in which two identical transformers are required. If this is one transformer and if this is the second transformer, to this transformer will act as load, and to this transformer will act as load. So in case of Sumpner's test, there is no requirement to connect the load because transformer itself acts as load on the other transformer. Therefore, the third reason is to save power. In case of large transformers, temperature rise determination. So these 3 points will tell us why to use Sumpner's test. Now let's discuss why Sumpner's test is also called as back-to-back test. And why Sumpner's test is called as back-to-back test means, in simple statement, one transformer will act as the load on the other transformer. That is, to this transformer will act as load, and to this transformer will act as load. And that you can understand from the circuit diagram of Sumpner's test. But it will be little confusing if you observe the circuit diagram of Sumpner's test. To understand that, little knowledge on Hopkinson test is required. Let's discuss that. Hopkinson's test is used to find the performance of DC motor, and this Hopkinson test is also called as back-to-back test. And if you can understand why this Hopkinson test is also called as back-to-back test, you can simply understand why Sumpner's test is also called as back-to-back test. Hopkinson test requires two similar DC machines. One machine will run as motor and the other machine will run as generator. Let us suppose this machine is acting as motor, and let us suppose this machine is acting as generator. If suppose the input supply is given to this DC machine, so as electrical energy input is given to this DC machine, this machine will run as motor. So the output from the DC motor is mechanical energy output. And if you give this mechanical energy output to the generator as input, that is by coupling the shafts of motor and generator, you can provide the mechanical energy input to the generator. And as now this machine is receiving mechanical energy input, this machine will run as generator. So the output is electrical energy. And if the electrical energy output is fed back to the DC motor as input, ideally there is no requirement of this input source, because in ideal case input is equal to output, that is loss are zero ideally. Let us suppose motor requires 10 as input, so by using some external source you apply 10, and then the output is 10 from the motor, and let us suppose this generator requires 10 as input, so this 10 is given to this generator and the output is 10 because we are considering ideal case, and this 10 we are feeding back to the DC motor. So now as this motor is getting output from the generator, there is no requirement of this external source, so you can disconnect this and these two machines will run continuously without any external supply. But is it practically possible to run these two machines without any external source? No, because of losses present in the machines. This requires 10 as input and let us suppose this requires 10 as input, and because of losses the output from the motor is 7, and this output from the motor is not sufficient to this generator. So here we need to give additional input to this motor to get 10 as output, and that 10 as output is given as input to the generator. Means we need to give the input to the motor which is equal to the losses in that machine. And now by giving the external input to the motor, let us suppose we are getting 10 as output. So this 10 as output is given to the generator, and because of the losses in the generator we will get again output less than the input, and this output is not sufficient to give as input to the motor. So to make the output of generator as input to the motor, again we need to give an additional input to the generator, and that additional input is equal to the losses in that machine. So to make this set run continuously, we need to provide an additional input which is equal to the losses of that machines. That is, here input is equal to the losses of motor plus loss of generator. So if you can now provide input which is equal to the total loss of that machines, now this set will run continuously, and as the output of motor is fed to the generator and the output of generator is fed back to the motor, so this test is called as back-to-back test. And coming to Sumpner's test, Sumpner's test is also called as back-to-back test because there we are making use of two transformers, and one transformer will act as load to the other transformer. So that's why Sumpner's test is also called as back-to-back test. And let's understand that with its circuit diagram. This is transformer 1 and this is transformer 2, which are similar transformers, and these two transformer primaries will receive input from the AC input supply through a single phase variac. And to measure the input power taken by these transformers, we are connecting a LPF wattmeter. This is LPF wattmeter. So now the input is given to this primary of the transformer, and the primary of transformer 2 is connected like this, which means primaries of the transformers are connected in parallel, and the power taken by these two transformers is combinedly read by this LPF wattmeter. And the important point that you must make a note here is that the secondaries of these transformers are connected in series with phase opposition. That is, the end point of this transformer is connected to the end point of this second transformer, and the other end of transformer is brought out like this. Means these two are connected in series but they are connected in phase opposition. Means they are connected in subtractive mode, and to connect in phase, the end point of this is to be connected to the starting end of this transformer. But here in Sumpner's test, these two transformers are to be connected in phase opposition. So now if you measure the voltage between the starting point of this transformer 1 and the ending point of this transformer 2, then the voltage reading must be 0 if they are connected in series phase opposition. And why they are to be connected in series phase opposition, let's discuss that in the discussion on how to perform this Sumpner's test. Now here our focus is why Sumpner's test is called as back-to-back test. So let's discuss that. And the secondaries are supplied from an auxiliary source, that is here a single phase variac, and this input is measured by using an UPF wattmeter. So this is UPF wattmeter. And now observe that, let us suppose that input is provided from this side. So this transformer 1 receives the input supply from this side, and as this side of transformer receives power, so this power is transferred to the other circuit, means this side. And for simplicity, let's forget this circuit, and now check that the output of this side is being received by this transformer 2 as input, and as this side of the transformer is receiving power, so this power is transferred to this circuit. And similarly, to make this side simple, let's forget this circuit. And now observe that the output received by this transformer is being fed to this side of transformer 1, which means that the power from this side is transferred to this side, and the power from this side is received by this side, and which is transferred to this side, and the power from this side is being fed to this side of transformer 1, which means one transformer will act as load on the other transformer. Means this transformer's load is this and this transformer load is this. Because of this reason, Sumpner's test is also called as back-to-back test. That is, because of each transformer acting as load on other transformer, this test is called as back-to-back test. Now let's discuss how to conduct this Sumpner's test. We know that this is the transformer 1 primary and this is the transformer 1 secondary, and this is the transformer 2 primary and transformer 2 secondary, and these two transformers are similar transformers and they receive power from the same supply. Let us suppose this is phase and neutral. So this transformer primary is receiving supply like this, and this transformer primary is receiving supply like this, which means transformers primaries are connected in parallel. And to measure the input power, we are connecting an LPF wattmeter, and to measure the input voltage, we are connecting an voltmeter, and to measure the input current, we are connecting an ammeter, and this total circuit is receiving power through a single phase variac. Means this is the single phase variac and this is the input AC supply, and the secondaries of these transformers are to be connected in series phase opposition. And if to connect in series and in phase, the end of the transformer is to be connected to this starting end of this transformer. But here we require the series connection of transformer in phase opposition. Means this end is connected to this end of the transformer. As now the secondaries of the transformer are connected in series phase opposition, and if you measure the voltage between the starting end and the finishing end of this, you must get the voltage as 0 because they are connected in phase opposition. As these two are similar transformers, the voltage induced here is equal to the voltage induced here, and as these are connected in series phase opposition, they both are equal and get cancelled each other. Means if you measure the voltage between this point and the end point, the voltage must be 0, and to check that we are connecting an voltmeter. So if the voltmeter reads 0, then we can ensure that these two transformers are connected in series phase opposition. And the important point that you must keep in mind here is that the voltmeter range must be double the voltage rating of this transformer, because if V is induced here and if V is induced here, if they are not connected in series phase opposition, then the voltage between this point and this point will be 2V. Therefore, the voltage range of this voltmeter must be double the voltage rating of this side. And to measure the current, we are connecting an ammeter, and to measure the power, we are connecting an UPF wattmeter here. And the secondaries of these transformers are supplied by an auxiliary source. So let us suppose it is supplied through an single phase variac. So AC input supply. So phase and neutral. This is single phase variac and this is also single phase variac. And if you connect a switch like this, this completes the circuit diagram. Now let's see the procedure to conduct this Sumpner's test. The first step is, with switch as open, that is with this switch as open, apply rated voltage on primary sides of the transformer. That is, we need to apply the input supply by varying this variac till the voltmeter reaches the rated voltage, and here the rated voltage value is LV voltage. So we need to vary the variac till the voltmeter reaches LV value with switch as open. And once the input supply is applied to this transformer 1 and transformer 2, EMFs will be induced in the secondaries of these transformers. So let the EMF induced in transformer 1 secondary be E2A, and let the EMF induced in the transformer secondary be E2B. And as these two transformers are similar transformers, so E2A is equal to E2B. And as these secondaries are connected in phase opposition, E2A and E2B will be cancelled. That is, if you measure the voltage from this point and the end point, the voltmeter reads 0. If this voltmeter reads 0, this indicates that these two secondaries are connected in series phase opposition. And if you view from this side, this will look like an open circuit test. And many will have a doubt in mind that if voltmeter reads 0, then it is short circuit. So how we can call it as open circuit? And the answer is that if short circuit, the resultant voltage is 0. But the converse is not true. 0 voltage doesn't indicate short circuit. That is, if suppose you are connecting two batteries like this, so these two are connected in series, and if you measure the voltage from this point and this point, the resultant voltage will be 2V. But if you measure the voltage between these 2 points when these two sources are connected like this, then the voltage is 0. And this 0 doesn't indicate that these two are short circuited, right? Here 0 means these two are connected in opposition and these 2 points are not short circuited. There is a lot of difference between the short circuit 0 voltage and this 0 voltage, and this is what happening here. And now let's discuss by viewing from this side how this can be as open circuit test. In open circuit test, HV side is left open and on LV side rated LV voltage is applied. And to measure the input power taken by the transformer, LPF type of wattmeter is connected. And to measure the input voltage, voltmeter V. And to measure the input current, I0, ammeter A. And it is taking supply from a single phase auto transformer. This is AC input supply. As this is open circuit test, that is, as secondary is left open, so current I2 is 0, and because of which transformer will drag very low current from the input supply, that is 4 to 5% of full load current. We know that input is equal to output power plus losses, and the major losses are classified as copper losses and iron losses. And as here open circuit, so current I2 is 0, which means output power is 0. So input can be taken as equal to copper loss and iron losses. And in open circuit test, as the transformer drags 4 to 5% of full load current, which means that copper losses are very low, because copper loss depends on the current. So copper losses can be neglected. So input power can be taken as equal to iron losses. And here we are using LPF type of wattmeter in open circuit test to measure the input power. So as input is equal to iron losses, which implies that this wattmeter reading will indicate the iron loss of the transformer. And the point what you must make a note in open circuit test, that here secondary is left open, means current I2 is 0, that is secondary current I2 is 0, and this is what we are making use in Sumpner's test. So as these two are similar transformers, so EMF induced in this secondary winding and EMF induced in this secondary winding are equal and opposite, so they get cancelled, which means voltage is 0, and because of which there will be no current flow in this circuit. So this will resemble like an open circuit test, because in secondary current is 0. So these two transformers will drag very low current, that is 4 to 5% of its full load current, by which we can neglect the copper losses, and therefore we can take input is equal to iron loss of the transformer. And here in this test, wattmeter will read the iron loss of these both transformers. So if you want to know iron loss of this one transformer, you can divide the wattmeter reading by 2. And now the third point is close the switch S only when Vs reads 0. That is, you must close this switch only if the voltmeter reads 0 reading. If it doesn't read 0, which indicates that these two are not in phase opposition. So we must interchange the terminals such that voltmeter Vs reads 0, and once this reads 0, you must close the switches. And now apply rated current by varying variac 2. Now by varying this variac, you must apply the rated current. Rated current I is found by rating of the transformer divided by HV side voltage. And it is known that rated current is obtained at very low input voltage. So you must vary the variac very slowly such that ammeter reads the rated current. And observe that when the input supply is given to the secondaries, now current I flows, and this current I flows through this secondary, and observe the current flow direction in this winding. So these two are opposite, and once the transformer 1 secondary receives power, this power is transferred to the primary side. And similarly, once this transformer 2 receives power, this power is transferred to the side. As these two secondaries are in phase opposition, so the currents in primaries will be in opposite direction, and the currents are limited in this closed loop. To understand that, observe this diagram and let's forget this circuit. So now let the current in this winding be in this direction, let the current in this winding be in this direction, and this can be furtherly simplified like this. So if one winding current direction is like this and the other winding current direction is like this, so observe that now the current will circulate in this loop, which means this current is limited in this closed loop and which will not flow in this wattmeter. Means this LPF wattmeter will continuously reach the iron losses. That is, variation of this supply doesn't affect the wattmeter reading, because by varying the supply, the power which is transferred is limited in this closed loop. It doesn't affect the wattmeter reading. Therefore, wattmeter reading will continuously indicate the iron loss of the transformer. And if you observe from this side, this input power is equal to output power plus losses. And here the output which is on primary side, and there is nothing to consume that output power, means this power is limited in this circuit, which means output power is 0, and the losses that are present are copper losses and iron losses. And we are applying the rated current, and that rated current is obtained at very low voltage, and as iron losses depends on the voltage, and here the voltage applied is very low, therefore iron losses can be taken as equal to 0, which means this input power can be taken as equal to copper losses. And here we are making use of UPF wattmeter to measure this input power, and here as input power is equal to copper losses, which means this wattmeter reading will indicate the copper losses of these both transformers. And if you want to know the copper loss of any one of the transformer, divide the wattmeter reading by 2. Therefore now the fifth step is, upon applying the rated current, now note down meter readings, and then by using these meter readings calculate percentage regulation and efficiency. Therefore, if you view from this side, it will resemble like an open circuit test, and if you view from this side, it will resemble like an short circuit test. But this Sumpner's test is entirely different from the open circuit test and short circuit test. And simply the procedure to conduct this test is that first you must ensure that variac 1 and 2 are at minimum position and switch as is in open position. Now vary the variac 1 till the voltmeter reads rated LV voltage, and now observe the voltmeter Vs reading. If voltmeter Vs reading is 0, then continue for next step. But if it doesn't reach 0, which indicates that the secondaries are not in phase opposition, then you must interchange the terminals such that Vs reads 0, and once Vs reads 0, now close the switch. And once the switch is closed, now by varying this variac 2, slowly apply rated current. And once the rated current is applied, now note down all the meter readings, and by using these meter readings find out the efficiency and regulation. This is how Sumpner's test is conducted. Now let's see how to find the efficiency and percentage relation. Here this ammeter reading is represented with I0 and this voltmeter reading is represented with V0 and this wattmeter reading is represented with W0 and this ammeter reading is represented with ISC and this is represented with WSC and the voltmeter reading here is represented with VSC. Therefore, note down V0 reading, I0 reading, W0 reading, VSC reading, ISC reading and WSC reading. W0 reading represents the iron losses of both transformers and WSC represents the copper loss of both transformers. And it is known from the open circuit test by using these three datas you can find the shunt branch elements R0 and X0. And by using this data you can find the series branch elements R01 and X01 or R02 and X02 and each transformer shunt branch elements are equal to R0 by 2 and X0 by 2 and each transformer series branch elements are equal to R01 by 2 and X01 by 2 or R0 by 2 and X0 by 2. And it is known that efficiency is equal to output power by input power and which can be taken as equal to output power by output power plus losses and which can be taken as equal to output power by output power plus copper loss and iron losses and output power is the rating of the transformer and WC is WSC by 2 and WI is W0 by 2. So place rating of the transformer and copper loss of each transformer and iron loss of each transformer. This is how you can find the efficiency and percentage relation is equal to I2 R02 plus or minus I2 X02 by E2. E2 is the secondary side rated voltage and I2 is the ISC current and R02 and X02 are the series branch elements and by placing these data values here you can find the percentage relation. So this is how the efficiency and percentage relation of transformer are found from Sumpner's test. Thank you for watching. If you like this video, please like this video, share this video and do subscribe to this channel. Thank you. See you in next lecture.